Evening, everyone. We're live on our tonight's Facebook Live, all about low temperature systems. And I'm joined by Richard and Rob. They can introduce themselves in a minute. Many of you already know Richard and Rob, I'm sure, but I'm sure there's some newbies out there who'll be joining us to have a look. We're missing Kimbo, but he may join later. You might be surprised by his face popping up later on. Yeah, so tonight we're going to talk all about low temperature systems and what that means, how you implement them, what is involved in that, and all of the sort of checklist of what you guys need to do to make this happen, and then obviously how that affects the future and where that takes us in the system and the whole run up to this heat pump installations that are inevitable and going to happen in time. So guys, do you want to introduce yourself and then we can crack on?
Hi, I'm Richard Burrows. I'm from Mid-Wales Plumbing Heat Supplies, regular to the show, grown a beard, as I said last time, and coming to you from Starlink, so outer space tonight. So hopefully Elon won't let me down, but you never know. I might get cut off mid-transmission and never come back. So let's crack on.
Hopefully not.
Yeah, hi guys, I'm Rob 𝗵𝗲𝗺𝗃, again regular to the show. Did miss the last one unfortunately, but yeah, just really into this kind of thing now, and I think it's really gaining traction about getting low temp systems and squeezing the best amount of efficiency out of the ones that we've got and the ones that we're going to be putting in. So yeah, looking forward to this.
Great. So should we start at the beginning? Like, what's the most important thing to do if you're going to implement a low temperature system in your customers' homes?
Well, the first thing you've got to do is quantify what you're going to need. So you've got to quantify the building. That, as we've said, is historically what we've not been doing, and we've been guessing. But we've been guessing because, frankly, a lot of the fossil fuels that we've been using over the last, 50 years or so have been very, very forgiving. Gas, you can, as we all know, you can fit a 40 kilowatt unit in the space that only requires 2 kilowatts of heat load, and it will still work. But if you do that with modern technology or modern heat pumps and systems, it's just not going to work. You just will not get the efficiencies out of the system. So oversizing is not an option anymore. In fact, I would always argue that with low temperature systems on heat pumps, you want to almost slightly undersize them to get these compressors running for the longest amounts of time. That's my personal opinion, but it's literally heat loss calculation has got to be done the very, very, very first, and that doesn't matter whose software you use or whatever. You can use free software just to do a whole house if you're just sizing the plant. But if you want to do room by room to actually do the system design, which is the second part of the puzzle, then you've got to do a room by room. So get your heat loss calculation done first. Once that's completed, then it's about system design or improvements to insulation throughout the building or windows, those sorts of things. I would also advocate now, depending on the sizes of the projects that we get, because you can lose between sort of 10 and 50% of all your heat loss out of a building if your air change rates within that building are quite excessive. It was quite upsetting actually to see the new building regs come out last year, where the air change rates acceptable in new builds was up to 10 air changes per hour. If you just work that on a basic mathematical equation, if you had a 100 square meter property with a 2.4 meter high ceiling throughout, that's 240 cubic meters. You times that by 10, that's 2,400 cubic meters that building could leak every hour and still pass building regulations, which is just ridiculous. And what really annoys me about that is that they only improve the regulation by 2 cubic meters. So it's up to 8 air changes per hour at 50 pascals now, which is the new building regulation, which I just think doesn't go far enough. So if you really want to get on top of this for projects that you're going to calculate, and it's only a couple of £100 to do, go and get a blower door test done as well. And with particular software like ours, you can actually then input those bespoke air change rates and drop your heat loss down by anything up to 50% of the actual heat load of the property, which is a win-win for everyone. Probably the best £200 you'd ever spend.
Will everyone know what air change means?
No, probably not.
Because I don't, but that doesn't necessarily mean no one else does.
It's the permeability of the building fabric at the end of the day. So and we lose quite a lot, as I say, but up between 10 and 50% of the actual heat loss of the building. Now, as newer buildings get more have less fabric heat loss. So, you know, they've got better insulation in the walls and that sort of thing. Those U values become smaller and smaller and smaller. So you actually got less of a heat loss through the fabric. But if the air changes on, even under current new build regulations of up to 8 air changes per hour, it's just showing you that the permeability of this building, of how, in other words, how it's put together, poorly fitted windows, maybe doors not fitted nice and snug, insulation in the roof spaces not meeting the cavity insulations and stuff like that, thermal bridging, all those sorts of things. You lose a hell of a lot of that there. So if you put mechanical heat and ventilation recovery into these buildings, and most of these units now, and there's proven data on it, can actually recover up to 92% or 93% of that ventilation change rate, which is, in my opinion, it's a complete no-brainer. I would say that the 𝗵𝗲𝗺𝗃, if people aren't involved with 𝗵𝗲𝗺𝗃 at the moment, get involved in it, because I think it's going to be the biggest growth industry in our heating industry of anything at the moment.
Great, thank you. I think I sort of understand what you mean.
Yeah, sorry, that was a bit over a mile an hour, wasn't it?
Whirlwind.
Yeah,
I got a little bit.
Yeah. Very happy. I mean, if people have got specific questions about that, put them in the comments, and I mean, I think you've put our email addresses up, haven't you? People can email us if they want to. I don't mind.
We can definitely do that later.
Yeah, we can answer some of these questions or help with this sort of advice, but there'll be quite a bit on our website. I'm pretty sure Rich has got some information on his website as well.
Yeah, I think the ultimate difficulty is in existing properties where it's older properties as well, because obviously there's, you know, by the 2010 building regs and, you know, sort of up to then, and then past and post and pre building regulations up to that, it was quite sketchy, and, you know, you're gonna always struggle with that without an air permeability test. So actually have someone come along, put a basically what they do is they seal all the apertures up that leak in normally, close all the doors and windows, and then have an air blower in the door and actually try and depressurize the house, isn't it, Rob?
Yeah, they press 50 pascals. I think it's 5 minutes each way. So they suck all the air out of the building and then blow air into the building. And what we normally do, if I'm going out to do an inspection on one of these, I'll take my thermal imaging camera, use the suction side of the pump, so it's sucking the air out of the building
to see where the leaks are.
And I go around with the thermal imaging camera, looking all around windows, and you can see air being drawn in from outside, so you know where the highlights are that need sealing up.
Yeah. Right. Yeah, we had similar with ours. So when we built our house, ours was a 2010 design, and when we built our house, you know, we had to have ours, you know, air blower tested at the end of it, and yeah, we got. I can't remember what the result now was. It was very good though. And yeah, same thing when they depressurized it, we went round and we actually, you know, you could feel the air coming in some of that, you know what I mean? Even though you've done a really good job on sealing the house up, we got some oak features in our house, and you feel by the oak, and you actually feel it coming through the splits in the oak, and you're like, oh my god,
yeah,
complete opposite.
So annoying.
Complete opposite to what you've sealed up to the oak and round it, and then it's actually leaking through the oak. You're like, what the hell is going on?
Yeah,
but you know,
oak always moves as well, doesn't it? That's the thing.
Nightmare. Yeah. Never build with oak. If anyone's building a house, never ever build with oak. Just literally stick some blocks in, paste them up, and you know what I mean, you'll be away, mate. So yeah, don't build with oak.
But I think the thing is that we the lower the flow temperature and the lower the system design that we can go, the more efficiency you're going to squeeze out of it. You know, that's kind of fairly obvious, isn't it? You know, if you're heating a bowl of water up that's lukewarm, it doesn't take anywhere near as much energy as it does to heat it up to boiling point. You know, and that's all you've got to think about it. And so, you know, if we want to live at 21 degrees nice and comfortably, theoretically, we could actually have a flow temperature of 22 degrees. You know, within because it's only just got to be above what we're trying to achieve, you know, at that point.
And I do make most of
the which is superb.
And I do actually. What I'll do is I'll put some of the data. I'll collect some of the data actually, because I've got a sensor at the top of the buffer over here. I can actually show that a lot of the time we get 21 and a half degrees. We get the solar thermal in the system heating this buffer up to 21 and a half degrees. As soon as it hits 21, it starts pumping it into the house, right?
Brilliant.
So you'll be amazed what that actually does. So if you pump it in there over an 8-hour period, even though it's only 21 and a half degrees, because the house is so well insulated, like the room temps, we'll go over there with a bit of solar gain as well. On a sunny day midwinter, we're like going there, we're like 23. It's like, oh my, do you know what I mean? You like cooked yourself in the middle of winter for free. It's like, what the hell? You know what I mean? So
Amazing.
I think what people have to realize, what people have to realize and get into their heads is that the lower the temperatures you go, 9 times out of 10, I don't know whether Rich might be able to answer this, whether it's linear or not, but the more volume of water you need to maintain the same set point. That's the thing. So that's why we have to have bigger radiators, for argument's sake, the lower the flow temperatures we go. Or if you can, I mean, I know, I don't know if you supply them, Rich, but there's quite a lot of companies out there now that are doing overlay underfloor heating systems, which are really quite good. I think the whole profile is under 18 millimeters thick, isn't it? Including
18 mil, yeah, we
18
build
mil,
up height.
Amazing. So if there's retrofit projects that people are thinking about and they want to go real low temp, I think for the price of it, taking up carpets and laying this down and putting a wet screed over the top is a really, really good option.
Yeah, totally agree. I mean, there's just so much. I mean, it's all about the design though, so it's really key critical if you're designing this up front, and even if you're putting a gas boiler or an oil boiler system in right now, and but thinking about actually, well, you can still achieve low temperature design and think about that actually in the property itself, but obviously some of the key things is you've got to match up your input with your output. So if you've got high heat loss rooms and things like that, it's really a chat with the customer about thinking about if there's possibilities to insulate those properties or those particular rooms, actually just to bring that heat loss down, so you can actually you can actually then design it with lower flow temps in mind. That's really, really key because obviously
it's understanding the fabric, it's understanding the fabric of buildings. So it's tools that we need. I mean, I think we've said this before on this podcast, is that you've got to have some sort of understanding of what the building fabric's doing, and you can do you're going to need different tools for this sort of job. If you want to get involved in just doing designs, you're going to need to specialize in buying some, invest in some decent tools in the sense of thermal imaging, maybe even get blower door testing equipment, that kind of stuff. I mean, something interesting happened a little while ago. My business partner Rich, we work quite closely with Build Test Solutions doing HTC measurements, which is heat transfer coefficient measurements, so real-time measuring of the building. What we did is we did a comparison between our software and the HTC software and input that did. But what we did, I mean, obviously it's Rich doing it, so we've gone right the way down to a fine-tooth comb of the materials we've got, the U values, and ours is modeling software at the end of the day. HTC is real-time measurement of the software. You've got to be very careful where you place the sensors throughout the property, that kind of thing. But it was unbelievable that actually both calculations came out within watts of each other. I mean, like I think about 15, 20 watts of each other. It was really not a lot at all. Actually might have been a bit more, might have been 100 watts. But it was nothing. And when you're looking at that, from us, it means that, really both of these things need to be done. I think HTC measuring is really, really good, but you do need a minimum delta T of, I think it's 12 between inside and outside for it to work. So unfortunately, it's seasonal, but it does give you a lot of confidence that both the modeling and the HTC measurements all correspond to each other when done correctly. So I think it's a great move forward, really, with this of getting this accurate design. Now, I've always said, obviously, it's got to be the calculation of the heat load first of all. Tell you what you want to do with any new window installations or insulation upgrades, that kind of stuff. Then it's the system design for whatever your end building fabric project is going to be. Once that system design is done, the very, very last thing you want to be thinking about is what's the most appropriate heat source, and that's it.
Yeah.
So it's a three-prong attack to it to get down to the low temperatures, and all we're seeing now is that the people that are designing these really low flow temperature systems are the ones that are really winning all these really juicy projects and getting these really exciting projects to do. So, if you're into your job, which you should be, because if you're not into your job, go and do something else. Life's too short to not be enjoying what you're doing. See and go as low as I can. I know our mate from Wales, 𝗵𝗲𝗁𝗆𝗵𝗁, he's down like 25 degree flow temperatures on most of his jobs, isn't he? I think there's like a little competition going on with these guys to see who can get the lowest.
That just makes it more interesting, doesn't it? If you're doing that kind of thing and creating these new systems that are lower flows, it's going to make
you're taking the guesswork out,
isn't it?
You're taking the guesswork out. You're giving yourself confidence, because when you've done the maths, and the maths are very simple, when they're even simpler if you're using software tools like ours. But if you get the maths done, and then when you fire the whole system up and it's all comes up to temperature at exactly the same time, it's all doing exactly what you said it was going to do. The pumps are not over, deadheading themselves and stuff like that. It's all running nice, sweet and open, just ticking along. It's a brilliant feeling. It really is a great feeling when you've done that design. You know that you've done all the maths and it works. It's like, oh wow, the maths don't lie. And for those of us who've been doing it for a while, we know that they don't lie. So
and happy customers.
Very happy customers. That's what I'm saying. These guys win all these really good projects. Because the clients are saying, well, my neighbour's bills a year are sort of £5,500–6,000, and mine is like 1,200 quid, or that's a bit of exaggeration, but you know what I'm trying to say. That's exactly what it is. And of course, everyone's having to vote with their wallets these days because it's the cost of living crisis is just it's astronomical, isn't it, for most people?
Yeah.
Well, the reality is it can be. I mean, ours are about £1,200 a year. So our actual full electricity bill, and that we've only got an electric bill, and we've got 2 electric vehicles, is about 1,200 quid a year. So, and it, when you take all the energy, all the energy wastage products away from your house. I mean, this is still work in progress here. It always is with my gaff, unfortunately, because I product test a lot of stuff that we do as well. So unfortunately, my work doesn't stay at work. Yeah. So, it does show. I mean, where I started here, which was actually a manufacturer's mistake. So, I just talk about that a little bit. Is that when I was first went into renewables, obviously I was really unsure of where I needed to be or what I was actually doing, to be honest, because we were predominantly gas boiler and oil boilers, and we would install, service, breakdown on those. And when we went over to renewables and they started talking about higher flow rates, this, that, now, I was really not sure what I was doing, to be quite frank. And so I went actually to 𝗵𝗲𝗁𝗃 and 𝗵𝗲𝗺. So 𝗵𝗲𝗺 did the underfloor heating designs here. They knew I was having a heat pump fitted and everything else. So we went to 𝗵𝗲𝗺 for the designs. We went to 𝗵𝗲𝗺 for the design of the sizing of the heat pump, actually. So they actually took our plans of our building and actually sized the heat pump to the our heat load and stuff. And so we ended up with this equipment here. And actually, when I was installing it, I was like, why have they put fixed blenders on the underfloor heating when it's a heat pump system? Do you know what I mean? And you're questioning them. They said, "Oh no, that's standard practice. That's how we do it." And I'm like, well, the heat pump can't get over 45 degrees, so why? I don't understand why we're putting high temperature blenders and stuff on a. And they were like, no, you've got to fit it like that. So anyway, so it ended up here. We literally had like heat pump with a shunt pump in it, pumping it to the buffer. We then had a pump off the buffer, which was then pumping it to the underfloor heating. And then we had 2 pumps on the underfloor heating, which then, do you know what I mean? So
this is like, the thing, isn't it? This is exactly the thing. When as you go in lower flow temperatures, you're generally going much more squeezed delta T, so therefore higher flow rates. Yeah. If you've got higher flow rates and so lower flow temperatures where you don't need blending valves, a lot of these blending valves are probably going to need 20 kPa across the valve.
Yeah.
So you're actually now saying that your pump running costs are going to be considerably higher, which is kind of defeating the object of what we're trying to do. So you really want these kind of less is more philosophy of everything open loop and all running around just nice and easy with hardly any resistance to it. With maybe 2 or 3 kPa resistance to the whole system. Which is likely on a lot of these things.
Yeah. Well, when we put the steeble in, which is behind me, so when we put the steeble in, we obviously it's got an internal pump, so that still pumps to the buffer. But what I did when we put the steeble in, I took all the blends, because obviously I know a lot better now than I did 10 years ago. So we took all the blends off. I should have done that at the start. I should have actually used my own engineering judgment at the time. But we took the blends off, put them fully open loop. The house is all open loop, and we literally got 1 pump off the buffer now, and the 1 pump off the buffer does the lot now. So basically I've got rid of 2 pumps. The pump obviously in the steeble's now a low energy pump anyway, so although it's got a decent flow rate behind it, it's still low energy pump. The one replaced on the buffer now, that's a low energy pump, but still very capable of high flow rates. And everything's quiet now. The actual nice thing in our house now is I can't hear the underfloor heating pump anymore, because man, it used to be noisy. It used to, you know what I mean? It used to come on inside the house, and it used, you know what I mean? I'm very lucky here actually, because we got a bit of land and stuff like that. So we got a remote plant room here. So actually we've got a pre-insulated pipe that goes from the plant room here over to the house. And just nice now, the pumps in here, you can't hear the underfloor heating in our house anymore, which is one of the absolute beauties of it. Yes. And but just having a much simpler system. Obviously, we completely cleansed it here. We actually treated the water to the correct pH values and everything else, and it's all beautiful. There's no inhibitors in the system here. There's nothing. You know what I mean? We got it all right, and those are the key things. We degassed it as well here, so we degassed the system as well, which is also very relevant to low temperature systems. That obviously, if we're doing low temperature systems, actually the system water retains the oxygen content and air content a lot more than obviously hotter systems do. Exactly. So one of the key things to actually ensure, because I think this is what's happening out there at the moment, is some of these renewable systems going in, not actually being degassed. And I think that's actually having an impact on the actual fuel bills a little bit as well. That if they were actually degassed, I'm sure we would. Unfortunately, we haven't got any data really behind that. There's not been any independent testing, I don't think, like at Salford or anywhere else yet, has there, on the effects of water content, system water with a high air content, oxygen content versus. I bet there will be in Germany. There'll be a load of that. And in fact, why not? We should look that up and see if we could find something for next time, maybe. But yeah. I don't know how many times we say this. It's the cheapest component in any single system, and it's the one that we care the least about. Yeah. I don't understand it. It doesn't make any sense to me. And I know certainly now I've adopted this whole idea of chemical free. In all of these systems. And I mean, one thing to point out to guys that are listening is that the lower these flow temperatures go, and it is a linear drop on the graph, deaerators don't work. So once you get down below sort of 50 degree flow temperatures, which we're moving towards now, those deaerators will only work up to about 1 bar of static pressure. They won't go in, and we're going to be going at much lower levels than that. So you actually have to physically or mechanically take that dissolved oxygen out of the water. It's the only way you can get it to a proper pH. And a neutral pH in systems now, if you've got mixed metals, so if there's iron in there, copper, aluminium, whatever is in the system, you've got to get that pH to about 8.5. If you don't get it to 8.5 and under 100 microsiemens of conductivity, then you're going to be in trouble. Yeah. And we've already proven, haven't we, for the last 50 years, that even though we've had sort of BS7593 and all the rest of these chemical understandings or treatments, I'm not saying they don't work, but they don't work very well because there's no real science behind it, and then no one seems to be producing the data to back up what they're proposing, which is a little bit awkward for the industry. So I would rather go down the scientific route and say, look, well, we have actually proven, the VDI or the German way of doing things, and it does work. As simple as that. I don't know if I'd said this before, but I recently got rid of a property I had in Berlin, and that building was built in 1952 or 53, I think. I can't remember now, but it had all the original radiators in it, up to last year. It had the original boiler in it. From day one, 1952. All they did was take the oil burner out and put a gas burner in it, and it's never ever had a drop of chemical in it in its life, and it's absolutely perfectly running like brand. All the balancing valves are all exactly the same as they were. You see, I see systems over here that are less than 5 years old, and some of the balancing valves in commercial systems, they're all dripping through because the glands have been rotted through because they're overdosing with chemical. Yeah, my system here, mate, I'll be really honest. My system here, which was chemically treated, when I did it 10 years ago, when we pulled it apart here, oh my God, it was terrible. Was it? Really, really poor condition. So I think as we go low temp now, there's so much more to consider with the system. It's not, we can't be classing ourselves as kind of, white box fitters anymore, or what's the other slingers? Is it slingers? Is it or something people call people slingers? Hate that word.
I hate it. engineers have got a hard enough time as it is, to make money and make a decent standard of living for themselves and stuff like that. But properly trained engineers and qualified. I mean, we're talking proper qualifications here that people get, and they deserve to get paid decent money for it. It's as simple as that. You buy cheap, and you will literally buy twice. That's the problem. And I think as we move towards these lower systems, anything that is more high tech or high spec is obviously a little bit more high risk if you don't get it sort of bang on the money. And that's what we're just trying to promote. And it's the learning behind it is, well, blimey, if I can learn it, anyone can learn it. So that's the way I look at it.
There was some interesting discussion, wasn't there? And something really I hadn't really thought about before is where should we be designing systems to? If we're going in with an oil or a gas boiler now, where do we really want to get those systems designed to? I mean, so a figure got banty around because obviously if we concentrate more on mean water temperatures than flow and return temperatures, because obviously if we design for a mean water temperature of say, I don't know, 40, for instance. Do you know what I mean? That then, starts opening some doors, but obviously there's a bit of a trade-off, isn't there? Because obviously there's a trade-off between rad size and what customers will be happy with that side versus actually, where you can bring your flow to, your mean water temperature to. So it got banty around the forum, didn't it? 47.5 degrees, it got banty around the forum, wasn't a bad point. But obviously that meant then running a heat pump at 50-45, didn't it? Which is probably a bit on the upper side that we really want to be doing with that, isn't it?
I would say low temp systems are going to be sort of 7 delta T kind of maximum, really. Something like that. Normally about 5, I would have thought for those proper low temp systems. But as you're going to 55 degree flow temperatures on existing fossil fuel units, I mean, I've got mine set up when it's just first firing up, or after setback at night. Set at DT10, and that just the flow temperature goes down, and once it's all up to set point, my DT drops right the way down. It's down to about sort of 3, maybe 4, and I can't do anything about that because the modulation pumps inside it don't modulate down low enough to speed to the so it can dump its heat quick enough. That's the problem. I mean, that's another massive subject with low temperature systems that I think we really need to kind of look at. I know Rich and I have been looking, and Kim actually in the last week or so, at this pump company. I don't know if I can mention the name at all, but this pump that they've come up with now, it looks incredibly efficient for what is going to go on down to about 100 litres an hour, which is about 2 kilowatt, I think, something like that, which is so much better than the ones that I had previously found out about, which I thought was about 240 litres an hour was its minimum, which is about 5.5-6 kilowatts. So it's quite amazing, really, the differences that we need to do and get down to these things. So I think shame Kim's not here because I know that he'd have a lot to say about this. Is the sense that if we could find a pump manufacturer out there that did a 130 mil replacement pump that was had DT sensors with it that could modulate to whatever delta T that you wanted to set that to, I mean, I think that would just be a game changer, and you'd sell millions of them. You literally would. It's a no-brainer, isn't it?
Yeah, totally agree. But you'd want it to obviously go down as low as possible on the literage as well, wouldn't you? So so it'd be a really low literage pump, but also one that could DT control and flow and return as well. So it's
well, a standard 1550 pump, which is obviously 15 is the bore size, 50 is the resistance to head to, which is 50 kPa or 50,000 pascals. Your average heating system, even with microbore in it, etc., will rarely go above sort of 25 kPa. So less than half the head resistance that the smallest pump you can buy on the market will produce for you. So it's pumps are massively oversized, and there's that horrible statistic, isn't there? It's now, I've got this from IMI Hydronics, is that between 15 and 20% of the total electrical cost, or total electrical usage in the world is taken up by dead-headed or oversized pumps. I mean, you think about that, that's thinking that's trillions of pounds in money, that is being wasted through, pumps dead-heading themselves and not being able to have a nice open and free low resistance system to work with. That's going to be one of the biggest wastage things that we've got to overcome next, I think.
Yeah. Before we move on from mean water temperature, I think a question coming, Claire, did it?
Yeah, Paul Spence has asked that question. Shall I show it? It's big.
Do you want to get that up? Yeah.
As the output radiator is not linear to the MWT, at what point would you consider a minimum mean water temperature? Oh, I see. Right. Okay. Minimum mean water temperature. Well, again, it depends what the size of your radiators are. The radiator is the size to 𝗵𝗲𝗁𝗃, as Paul says, which is correct. But don't forget, the other thing with 𝗵𝗲𝗁𝗃 is that it's calculated at 𝗵𝗵𝗁𝗃, so top, bottom, same ends as you pipe it up. And in the UK, we pipe up to 𝗵𝗶𝗁𝗃 most of the time, bottom opposite ends, which is about 4% less output, Rich, isn't it? Is that right?
Yeah.
Yeah, 4% less output than 𝗵𝗵𝗁𝗃. So you've got to take that into consideration as well. We've got and I'm not trying to blow trumpets here, but we've got a really, really good low temperature radiator calculator tool on our website, which you can just put in any delta T that you want, any mean water temperature that you want, and it will tell you exactly what the outputs you'll get at those mean water temperatures for any size of radiator that's existing. And a lot of the time we find that most people have to maybe swap a K1 for a P+ or a K2. Or a K2 to a K3. I'm not a big fan of K3s. I've got to say, I just think they look ugly myself. But you know,
they're bloody heavy as well.
So. Yeah, they do your back in. Yeah, exactly that.
We've had to lug a few around the warehouse, and they're not much fun, I can tell you. So
no, I mean, look, radiators eventually sort of blend into the background, and people get used to them and don't say much. But I mean, I think it would take me a long, long time to get used to a radiator that's like 250 millimeter thick. You know. Yeah. It's you know, you got to push your sofa into the middle of the room, haven't you? And those sorts of things. But
yeah, you lose your front surface where your sofa's sat against it. Do you know what I mean?
Well, yeah, it's only about 10% of output, isn't it? Maybe
10%
of output. But yeah, it's I don't know if that answers your question, Paul. I hope it does. But if not, just bung another comment in the side there. But it's good. It's a good call. Good question.
So
no other questions. Yeah. Okay.
No other questions there at the moment. So talking about radiators and existing systems, let's talk about how we deal with what's in there at the moment. Do they need upsizing, or are they generally okay?
Well, there was an interesting video released this week by Simon, who's urban plumber on YouTube. And he's obviously a Heat Geek approved installer and this, that, and the other. But he's a very, very actual competent installer, and he fitted a Valiant heat pump aerotherm onto a. Basically, he did the calcs, and the calcs said that the rad sizes that they had basically were fine for the property to actually go a lower flow temperature. So actually, he didn't change them. Put the heat pump straight onto the system, and it works, but I mean, the important thing there is, and the important bit about that comment is that, he did the calcs. So he actually calculated the room by room calculation of the house. And then actually each of the radiators were capable of outputting the correct amount of heat at the, at the set flow rate, at the set flow temperature. Sorry. So, it was, it depends, doesn't it? It depends. Are you doing the maths up front? Are you calculating it? Are you doing it? Because you won't be able to guess it. You won't know. Do you know what I mean? You unless you actually calculate it out, you won't know for sure. Is the truth. So, in a lot of the time, go on, Rob.
I'll just say one thing to add to that is that we're kind of fortunate in the sense that most of the radiators that we have fitted up to date have been fitted aesthetically, so they've been fitted into window areas, so they're generally massively oversized to what they want to be anyway. And you can't oversize a radiator. Let's just say that what oversizing is a problem generally with the heat source, so the plant. Everything else, you can't oversize expansion vessels. That's fine. You can't oversize radiators. It just means with an oversized radiator, you can run it at a lower temperature to get similar output, or the output that you need for the room. And also, what we've been doing is that we've been generally oversizing pretty much all of the pipework that we've been putting in, because the biggest selling pipework that we need in the UK is a bundle of 22 and 2 or 3 bundles of 15 that you put in. And we've been putting that in as standard for as long as I can ever remember. And it's amazing how much you can get. I mean, you can run very, very low delta T, delta T5 systems, with an average heat loss on a building, 4 or 5 kilowatts, something like that, through 8 mil microbore, no problem at all. And you're still under 1 meter a second, which is the recommended velocity through these, and you might be up to maybe 350, 400 pascals per meter. But if you've got 400 pascals per meter and the smallest pump you can buy has got 50,000 pascals in it, you're not oversizing a pump at all. That's the thing, and it'll get over those resistances. So it's the maths. It's just understanding the very, very basic maths to get this right. But the majority of systems, as Simon, quite Urban Plumbers put up, which I think was a brilliant video to do, is that most systems will work at lower temperatures. Yeah, and I think you'll find, there's been this bit of confusion, hasn't there, with the fact of obviously turning down the flow rates, flow temperatures, etc. And the warnings coming out from people about Legionella and God knows what. And turning down the flow temperatures only really applies to combi boilers in that sense. If you want to pasteurize your hot water circuit, if you've got a hot water cylinder, you only got to pasteurize it once a week up to above 60 or around 60 degrees. The danger for Legionella, if anyone wants to look up the document, is 𝗍𝗁𝗍, is that the danger zone is between 20 and 45 degrees. That's when Legionella is really prolific. So 50 degrees will kill it, but to pasteurize the water, they like you to have a boil up every once a week of up to 60 degrees, and that is included if you've got secondary return circuits, which we're kind of tending to shy away from now if we can on lower temp systems, hopefully, because it dumps that heat into the heated space, which is kind of not really what you want to do. But yeah, that's sort of my look on it. So a lot of these systems will work, but certainly any combi boiler out there, you can set it to whatever flow temp you can. I mean, mine generally in my house now runs around 35 degrees on my boiler. And I've got a combi boiler, and I don't see the point in heating up a radial circuit that I've got coming out of my combi boiler to feed my shower in my bathroom and stuff. Why would I want it over 40 degrees? I can't get under hot water that's over 40 degrees because I'll burn myself. So what's the point in spending all that money to heat that damn stuff up, to blend it all the way down to something you can bathe in? It makes no point. It makes no difference to me. So that's the way I look at it, and that saves me a lot. As I said, by balancing. I mean, I use the pressure independent valves like you got on your 𝗍𝗁𝗍𝗶𝗴s. I use those throughout my house, and after everything was balanced, and I settle my weather compensation, load compensation right the way down to the minimum I could get away with from a heat loss calculation. I knocked nearly just over 6,000 kilowatt hours a year off of my heating bill. I mean, that's astronomical, especially now. Was it 35 pence a kilowatt hour now for electricity and about 10 pence kilowatt hour for gas, isn't it? So it's
for domestic, mate. It is. It's commercial's incredible actually, because we have our warehouse, we heat and electrify, and it's 80 pence a kilowatt hour for electricity.
Oh, really?
34 pence a kilowatt hour for gas.
Good Lord.
Wow.
So there you go. See that if there's not
commercial side, it's big money. And like I said, if you do flip over between domestic and commercial, you can make some real massive differences to commercial buildings actually. So there's probably actually more energy saving in commercial buildings that we can do than there is actually domestically. And low flow temperatures can come into that as well, because you can have low flow temperature systems in commercial buildings. Instead of these big, massive 54 kilowatt, space heaters that are there, blown space heaters, actually, you might be able to get something in there that you can have a fan convector that running at 35 degrees just for longer periods of time. And actually, you get the same effect, and it's funny, just turning things on their heads really, and just trying to maximize everything you can, and like Rob said, if just a bit of tweaking of his system saves that much money, it's amazing what you can do for your customers. And it's just literally tweaking the systems, and like I said, a bit of calculation behind it. I mean, if I was still out there, and I'm sad I'm not in some ways, because I would, some days I miss it, but if I was out there, literally all my customers, I'd be out there looking at the systems. I hate the fact I've got auto lights in here. They're too clever for their own good sometimes. But it's like, oh my God. But yeah, if I was out there now, I'd just be literally going through each of my customers' houses going, can I upgrade the system? You know what I mean? Walk in there, have a chat with the customer. What are your bills like? Let's have a look at your bills. What are your kilowatt hour usage? Everyone's got a smart meter now, so they should be able to go bam and give you that data instantly. And you have a little calc up and go, you know what? I think I can save some money here. And sit down, work it out. And if it's big enough, if they're going to save £1,000 a year on their fuel bills, and you look at it and you go, you know what? It's going to be a couple of grand's worth of work to upgrade it. You're going to pay back. You know what I mean? You're going to pay back in 2 years, and you're going to save money every bit from there onwards. Do you know what I mean? And it's just worth that conversation.
I'll tell you what we're seeing. I'll tell you what we're seeing now, as from Heat Engineer, is lots of members of the public buying single surveys and then doing the measurements in their own houses, and maybe calling local plumbers or whatever it is to come and have a look at them after they've done their own calculation and seeing what they've got, which is fine. But I'd always say use a professional to do it. But you can, as long as you can use a tape measure, and you understand a little bit about the building materials, you can get very, very close to the target of what you need. And if that is the case, I mean, the government have stated quite clearly that they want, I think it's between 6 and 8% net emission drops, or savings by 2028. I think it is something like that is the target. Well, that's not a big target. We could do that now. We could just with balancing systems up and setting lower flow temperatures as we've got, we could get that saving now. We could smash these targets easily. I mean, I think what's 𝗵𝗲𝗁𝗁𝗁𝗁𝗁 saying, there's 20 million boilers out there at the moment that aren't condensing. It's crazy. Since 2005, we took out perfectly good atmospheric boilers and stuck in condensing boilers that don't condense. So in other words, more atmospheric boilers. Yeah. So we didn't improve efficiency in any stretch of the imagination. We just lowered the water content by about 20 litres. Happy about it. Yeah. So it's kind of crazy, but I think the good thing is that the public are waking up, and I think the public will be the driving force behind this eventually, because they will say, look, we actually want to demand more. We do want to get the best out of this system that we possibly can, and it's crazy. I know people in similar houses to me. I mean, I'm at the moment, I've just put my standing order up now in my place. I think I'm paying about 160 quid a month now to my standing order for gas and electricity for my dual fuel. And I only live in like a Victorian cottage, so 2 up, 2 down cottage. But I know people that are living in a similar sort of size house. Mine's 3-bedroom actually, because I've done the roof space. But similar houses, mid-terrace, they're paying like 350 quid a month. And I'm thinking, well, how come you're paying that much money? You should be
the same house.
You should, for the same house, you should be able to half it. If I can do it in mine, you should be able to half it. And that is a significant amount of money when you're looking at it over a year.
Yeah.
So it can be done.
You have that irony, don't you? Literally 2 neighbours parked next to each other. One's got a good installer who's done some low temperature work and set it all up properly, and the next neighbour's got, some other company who's not bothered and drive-by services and stuff like that. And do you know what I mean? It's
I was only talking to a neighbour about 4 doors down about last weekend about this, and he said, would you come and have a look? I said, yeah, of course, I'll come and have a quick look and see what differences or changes you can make. So there's opportunity out there. I would say now in the heating industry there's more opportunity in the heating industry now than there's ever been in the and I've been in the game 40 years. It's just more now than there's ever been. I can't think of a better time in that sense for what can happen. And I think we're going the same way as a lot of Europe has gone, where our industry is going to split up. So you're going to get people that are either coming off the tools and just want to go into design work. You're going to get people that just do pipe work. You'll get people that don't want to do any of the design at all. I just want to do installations. You'll get people that just want to service boilers. You'll get people that want to do 𝗵𝗻𝗁, upgrading radiators, insulation, all sorts of blower door testing, all sorts of things like that. There's just so much opportunity now. There really, really is.
Yeah, you don't need to be a heating engineer anymore, do you? So you don't need to just have that badge and do everything anymore. You can literally afford to specialize in a subject, and actually you'd be flat out all the time, especially when it comes to design side now. It's quite funny. I was talking to 𝗵𝗲𝗁𝗁𝗁𝗁 actually, and he was saying, where's all the good guys gone? You know what I mean? He goes, where's all the good guys gone, Rich? And I said, they've all gone into design, mate. They've all gone into design or another place where the work's not that, that drag all day, and you try and push. You try and push crap uphill a lot of the time, isn't it? Because, ultimately, to get the best out of these systems, you've got to spend the money and you've got to actually do that. And the amount of customers that won't let you do that, or, you know what I mean? Or you think you're on price, or someone thinks they're on price. And then that's the bar that everyone gets set to. Do you know what I mean? And it's just such a shame, because, all that ends up doing is pushing the good guys out the industry actually into something else, when we need to keep the good guys in the industry, and there's...
Yeah, but also I think it's I'm certainly not ever want to slate engineers in the UK, because I think they get enough hassle as it is, and it's hard enough as it is. it's the upskilling. I think it's not engineers' fault that the education system has been the tick box culture that it's kind of morphed into over this last 50 years. It's now it's been really caught with its pants down, and it has to wake up. Really, I guess people, anyone that's sitting in on a podcast like this, they're making effort. They're making effort to try and educate themselves. And move forward, which is exactly what we've got to do. And as I say, if the public start to drive this, which I think they are, we're certainly seeing that that's what they're doing. And we've produced over 20, I think it's about 22,500 reports now. It's a lot of data, that we've done. And there's at least that amount of systems out there now that are at least sort of, partially calculated or much more efficient. And that's snowballing. We're actually seeing growth sort of like start to hockey stick now, which is good for us, but it's especially good for the industry. From what I can see, we got a clever post up here now. I'm 130 quid a month for both gas and electricity, 4-bed, 2-bath detached. Well, that's pretty good. Be interested to see how old the building is. Mine's 1905, just to let you know. Solid walls and leaks like a sieve. And
that's Paul again, Rob.
Oh, is it Paul again? Right, yeah. I'm on about 4.5 kilowatts. Mine runs about 35 degree flow temps. Yours is on 45. You got 3 zones as well, right? Okay, that's 2005. Okay, so it's a much more efficient building than mine is generally, I would say. But I mean that's still pretty good. I'd also say this as well is I am actually overpaying on mine by about probably 10 quid a month, maybe something like that. Because with OVO Energy that I'm with as a long-term customer, I get 5% interest on anything that I'm in credit. So it's better than putting your money in the bank at the end of the day.
Leave it in there.
Leave it in there, yeah, that's right. Let it accrue. But I can only see gas prices going up more. Possibly electricity prices will come down a bit. I don't know how much they're going to come down because the amount of
they're talking about parity, aren't they? A little bit more.
Well, they're trying to, but it is a very controversial issue, and in my opinion, you cannot run a successful economy on expensive energy. It doesn't work. You've got to have cheap energy in order to make it work. That's going to be a problem, and I don't think you can sway people's opinions on what heat source type they can do by pricing some existing out of the game. That's just not fair. That's just not fair. We got to have both of them cheap at the end of the day until we get the transition across to. And it's a no-brainer that electrification is far more efficient than any fossil fuel burning, because fossil fuel you're going to get the maximum about 90% or 0.9 COP out of your system. Whereas a heat pump, I think MCS basic minimum standard is 250%, isn't it? 2.5, is it 2.8? I can't remember now. I mean, I would say you want to be getting around 3.5 if you want to make a system sort of viable, really, as a starting point.
I mean, the shame of it is like the new bus scheme and stuff like that doesn't really support ground source heat pumps, anywhere near as it does air source. And like I said, the steeple behind me, I was monitoring the other day, and we're up in the 6s. Do you know what I mean? So
amazing, 600% efficient, brilliant.
Which is nuts. And most of the time it sits about the 5, COP 5, so it's 500% efficient. Which well, it's gaining that. It's not that efficient, but it's gaining it from the ground. Do you know what I mean? We're bringing 5 units in from the ground. And that's amazing, and when I'm paying, because I run mine off peak as well. So I actually, because my house is really well insulated, I actually charge it at night. So I charge it at night on off peak energy. So I'm paying at the moment on 𝗵𝗲 Intelligence 7.5 pence per kilowatt hour. So then if you then divide that by 6, you can see that I'm not actually paying that much pence per kilowatt hour. I'm certainly not paying 13p or 14p gas, you know what I mean? So paying 1 pence a kilowatt hour, you know what I mean? And when you lose that kind of technology, it's a shame, because like we're kind of, I appreciate monoblock technology and everything else is way up, it's much better than it used to be, and we are seeing some really high COPs on that. But just seeing some of the data monitoring, because I'd like to see the data monitoring of the COP 6 you just mentioned there. Because most of the data monitoring that obviously I've been seeing online with the I forget what's the link now. It's because Tristan and a few of the other guys on Twitter, and they've done a thing, haven't they, with the heat pump monitoring software and stuff that they do online. But I've been watching some of the COPs and stuff of the units that are running on there, and in the fours, which is quite acceptable for monoblocks. Do you know what I mean? As a which is very good. But obviously, if we can get the like I said, it's quite warm outside at the moment. So I mean, mine's going to be way up anyway because of flow temps probably into my system at the moment are in the 20s degree flow temps. Do you know what I mean? So it but it's interesting to see just seasonal performance actually on real heat pumps rather than actually suggested, or manufacturers, coefficiencies. But
I think as you were saying about, or we were talking about earlier, just before we came online, was that people trying to retrofit sort of PV and battery storage into their systems now. Certainly, if you're trying to get heat pump ready and low temp ready for the future, you can offset all your electrical running costs as they stand right now. But then once you do eventually go to a heat pump or a hybrid or whatever it is, because I think hybrids probably will eventually come into the bus scheme. It certainly looks like they will. That is another stepping stone that could buy us a few more years and certainly squeeze another 200 or maybe 200 or 300% efficiency out of our systems, which is a massive increase over the 6 to 8% net reduction that the government are aiming for. It blows all this stuff out of the ballpark, doesn't it? Which is exactly what we're trying to do. So that's exactly what I'm going to be doing.
Especially if it's free, isn't it, mate? Because if you've got battery storage and you've stored that energy, do you know what I mean? I mean, I generally. So mine's a bit more complex. So if we've had a sunny day, actually, I'll bring my heat pump on. If it depends what air temp it is outside, but I've got a little program that runs basically that if it's a sunny day and we've got plenty of energy, the batteries are charged, and we've got excess. Actually, I'll bring the heat pump on. Because if it's running on free energy, it doesn't matter what the COP is then, really, does it? Do you know what I mean? Ultimately, it's always going to be cheaper than direct electricity, and it's just maximizing everything all the time, and having that, that's the next step for low temperature, low energy systems is ultimately is having that intelligence behind it, and hopefully, manufacturers like Drayton in the future will have systems like that will, be intelligent enough to predict, not just react like the majority of controls do right now, actually predictive controls and actually maximize those low temperature systems that they can go, you design. And that's where the design comes in really important, is actually if you design really low temperature systems, especially with underfloor heating, that if you then get free energy to run those, even if you only get a small amount of energy, because like the beauty of heat pumps is they use very little energy anyway. So if you've got solar plus battery, and you say the heat pump only needs 1 kilowatt or something like that, you run it off the solar and the battery. Do you know what I mean? And you're actually not using anything, are you? But gaining 4, 5, 6 times the energy input into the heating system, which is exactly where you need to be.
I mean, there's a lot to be said now as well, because we haven't been calculating out heat losses for forever. I mean, we were using those very inaccurate 𝗵𝗲𝗁𝗁𝗍 calculators. I think I've still got all 5 of mine, all 5 of the different types.
How good are they? How good are they versus?
They're about 20% out, maybe a bit more. And I think you could probably get them a bit tighter, but they're not the best. And of course, the technology's moved on a hell of a lot since those times, now as well, especially with thermal imaging and blower door testing and stuff like that, to get even closer to the target is great. But because the heat losses are a lot less, than we initially thought. So my house is, typical house, 4.5 kilowatt, at -2. So it's really not a lot. But an air-to-air unit would be able to do these places, and if you've got some battery storage for doing that, so we don't just have to start thinking about the fact that we're still going to be transporting a load of water around the system. We might not have to do that anymore. We might only just become plumbers then, on the heating side of it. We're just using air-to-air heat pumps, or so you're more of an electrician than anything else. That's another option that we could be looking at some point in time. But if we are having to use water to transport the heat around, which obviously it's a very, very good material to be transporting heat around, and it holds its heat for a long, long time because of its specific heat capacity, etc. But if we are going to be doing that, we've got to really maintain the quality of it and maintain the system that it's going to be doing with the least amount of resistance running right around the system to get, as Kim says, the right amount of heat to the right place at the right time. And that's it, to keep it ambient. I know a lot of people, this is controversial again, but I really quite like open loop one pipe systems. I've always liked them for heat pumps. I think they're great. It's just a nice open loop. Yeah, you've got to have bigger radiators on the end of the circuit because you're a lower mean water temperature, but that's all you've got to calculate out, and it's easy to calculate out. So I really like them, with high lift valves on the sides, and away you go. Just let it run. I think they're brilliant with a compit, and it's the way it goes. It's so simple to do, but that's controversial.
Only on this chat.
Only on this, yeah, exactly.
We're always controversial on here.
Well,
There's well, it's all about giving everybody the bigger picture, isn't it? It's not just, we've always said that these aren't about Drayton products, are they? They're not necessarily about that. They're about, educating the guys out there on the ways that they could potentially do stuff better, or, different things that they might not have heard of, and all of that. And it's great. Tonight's session's been really great. I can't believe it's 54 minutes in already. I was just going to bring up, where controls sit in these low temperature systems, to kind of just have a little mention of them. But Rob's,
you're talking to the guru that's sitting up the top of the screen here.
It's a funny thing, isn't it? So because we're going with a gas boiler, to me, I always say control it to death, because if it's already a very inefficient product anyway. Like Rob said, it's COP 0.9 at best. Do you know what I mean? That's all we're going to get out of it. And I always think every piece of energy that you put into a system like that, we want to try and manage that best we can. Obviously small systems you can get away with just one circuit control, things like that. But as we go into low temp, it's a funny thing, because we've got to, like Rob said, we've got to work with the technology we've got. Heat pumps aren't as forgiving as gas boilers are. If you look at the modulation range on a gas boiler, look at 𝗵𝗲𝗲𝗺𝗀, you've got like an 18 to 1 modulation ratio, which is nuts. Do you know what I mean? It's, we can have an appliance at 30 kilowatts right the way down to 1.9 kilowatts. And it's crazy. That's a crazy modulation range. On a heat pump, we haven't got that sort of modulation range. We've only got about 20% modulation on total. So, if you got 10 kilowatt heat pump, we can only really modulate that output down to about 8 kilowatts, so it's not quite as good as we can get. So obviously the other end, because we multiply out, but you've got to think about that a lot, because ultimately if we've only got a very small modulation range, we've got to keep the flow rates quite high actually. So then when controls come about, we can't really use TRVs to wage areas off and stuff like that. And unfortunately we have to start thinking intelligently. So like my idea, or the future idea of controls, is that they will interact with the heat pump, like I said, to be more predictive. That's the only way controls can really go, because to make the best of heat pumps is actually to look ahead into the future and go, what's it going to be tomorrow? Is it going to be sunny? Am I going to be able to maximize the PV yield? So controls will be more than just controlling the heat source. They'll look at what yields coming ahead, because with PV, you can actually predict how much yield you're going to get in the next day. Yeah. Because if it's a clear sky day and where the sun's going to be, and you know what I mean? You know how much energy roughly you're going to produce based on the size and the orientation of your panels and this, that, and the other. So you can actually predict it. I've actually got predictive software that I use at the moment, and it says like tomorrow you're going to generate 30 kilowatt hours. So if you're in that scenario, but it's still going to be a cold day, you want a system that can go, what, you're going to produce 30 kilowatt hours of free energy. We're going to use it tomorrow. I need 15 kilowatt hours tomorrow of heat energy. I'm going to use 15 kilowatts of that 30 kilowatt heat. You know what I mean? And that's the way you have the system managed. And that's where controls are going to come along. So where we're going to actually probably lose certain controls, like TRVs, there's going to be more open circuit, and until the modulation range of heat pumps can modulate that vast, we're going to lose the proportion of things we do. Yeah, I'm not saying don't fit TRVs, but you'll need them as trimmers in certain areas. Certainly in high glazed areas, you're going to need to trim the air temperature a little bit. Yeah. But ultimately, you are going to have more open circuits. Our valves need to be, so that the things that do need to happen from a controls manufacturer perspective is that we're going to need better valves. You're going to need valves that can control the valve authority a lot better, things like that. Valve apertures. looked at, flow rates looked at, things like that, you know, design on valves looked at. And then from a control aspect, you know, because what I hear in the background from heat pump, you know, guys fitting some heat pumps, they're like, the controls are crap. You know, they're really ugly. They're not very user friendly.
Really complicated.
The UIs aren't very good, things like that. And it's really up to the control manufacturers to sort of come in with those people and go, look, you know, we're a controls manufacturer. We can produce something that's beautiful, but still operates perfectly with your heat pumps. And that would be a major step forwards, you know, things like that. That's the future of controls for sure, you know, and, you know, where the thing is, right, with people who are thinking about 𝗵𝗲𝗁𝗵 and stuff like that right now, that's where controls of the future will be. That, you know, we're not going to have this on-off switching scenario. We're going to have intelligent controls. You know, they're going to be bus controls, mode bus. You know, they're going to communicate, and that's the way they'll be. You know, we're going to be very much going away from on-off controls. So it's very important that you know, we do make sure as heating engineers that we're educating ourselves, and we're doing weather comp systems. We're looking at that control aspect a lot more and learning that side a lot more. Just ultimately, just to make sure we're going to be ready for it. Because yeah, you know, Modbus controls and things like that, they do come with, a lot of controls come with diagnostics, but that's another thing as well. You know, control manufacturers can help with that side. You know, give that diagnostic data back. You know, maybe with remote monitoring as well of the actual heat pump data and things like that. You know, I'm not saying it'll be heat pumps, it could be other things as well, but, you know, it gives that data feedback back to the installers. Those will be the best controls in the future, I think, you know. And maybe even, because I was talking to 𝗵𝗲𝗁𝗵𝗁𝗵𝗁 on Monday. I actually went to their training center looking at some of their new heat pumps and stuff, so that was quite good. And you know, having that diagnostic data, so when you fit your appliance and you go away, because you've not got time on site to actually monitor that, but it actually is you know, having computer systems actually that monitor the heat pump data and alert you as a manufacturer or a heat pump installer that, you know, something's not quite right here. So either something's got clogged up or something, do you know what I mean? Before the customer calls you, it actually gives you feedback of that data. That's really controls of the future. You know, that help you as an installer, that you can efficiently get around all these systems, do the jobs, leave the jobs, but actually have that intelligence to feed back to you. Look, this is actually running all right, or actually this isn't running all right. Something's wrong. You know what I mean? And you need to reattend, and just things we haven't got right now. But that's all you know, all of that's possible, and like in some instances are already happening. But you know, it's but that's it in a nutshell. You know,
I think to add to that, we've got to have more joined up thinking in this industry, really, when it comes down to controls, because there's just at the moment, I mean, what was that thing we were talking about before of all the different protocols that there are out there at the moment? It's you've got to have some kind of common language that everybody can speak, and let's make it an open playing field. It's about getting the efficiency out of the system, not about sales for a particular manufacturer. Oh, we work in this scenario, because you want everybody to be able to understand a language. It's like trying to control an army, isn't it? With all, you know, and everyone's speaking a completely different language. It's just not going to work. You know, you got to all be talking the same language in order to get some unity going on. That's how I feel. You know, to make it easier for the engineers and easier to get to the you know, reductions in emissions and better efficiencies that we need.
Yeah, lots of system using Modbus, so or heat pump systems. Lots of systems.
Choose one and everyone get on board. You know, that's
it's the common language thing, you know, should already be happening in gas boilers right now. You know, I mean, I'm amazed actually with 2023 and we still not got a common language between boiler manufacturers. You know, to make sure that whatever controls are fitted, you know, that they're absolutely maximising that product. Do you know what I mean? And that's just amazing that isn't happening, because we don't want that rolling into low temperature systems. You know, definitely not. That would be a massive mistake if that happens.
Yeah, I agree completely.
But
interesting.
Awesome,
cool.
Food for thought to guys. Thank you very much. Hopefully everybody's enjoyed tonight's session and got some useful stuff out of it. Thanks Richard, thanks Rob, always a pleasure and always so informative and useful. And I think we will close tonight's broadcast and we'll see you next time. Thanks guys. Bye.
Thank you everyone. Bye bye now.